Okay, great, great. All right, welcome to the HelioHub Solar Circuit, a series of presentations and discussions and workshops, all related to the wonderful field of heliophysics. And today is June 10th, and we have an expert panel for you. We're going to be looking at heliophysics research methodologies. If you were with us last week, you'll know that we are funded by the NASA Drive Science Centers, and particularly the first one here, COFFEES, which is based out of Stanford. COFFEE stands for Consequences of Fields and Flows in the Interior and Exterior of the Sun. But we're also very much associated with the other two Drive Science Centers, CGS, which stands for Center for Geospace Storms, and SHIELD, which is a kind of complicated, it's a real acronym, kind of complicated though. Just think of SHIELD as studying our sun's bubble, also known as the heliosphere. All right, and if you want to learn more, you can go to science.nasa.gov/heliophysics/DSC, which stands for Drive Science Centers. All right, today, heliophysics research methodologies. I wanted one slide to be quick to kind of tell you very briefly what we're going to be chatting about today. So I went to ChatGPT and made a request. I need a colorful image that shows a ground-based observatory, a spacecraft, and a computer to very generally demonstrate the idea that heliophysics data gathering is done by 1, observation, 2, particle and other detection via instruments, and 3, computational modeling. And I got this, which I thought was good enough. So today, with that focus in mind, we're going to first have my colleague from COFFEES from Stanford, Aimee Norton, talk about the observing side of things. And then also from COFFEES, but based at UC Santa Cruz, is Loren Matilsky. We're talking about the computational side of heliophysics research. And then another colleague, although not associated with COFFEES, but at the Space Sciences Lab at UC Berkeley, we have Hunter Kanniainen, going to be talking about instruments and detections, specifically kind of space-based detections. And with that, I'll stop sharing. And who's going to start? We'll start with Aimee. Who's going to introduce Aimee?
I can introduce her.
All right, excellent.
So Aimee is an astronomer who uses observations of magnetic fields in the solar photosphere to study the dynamics of sunspots, the solar dynamo, activity cycle, and MHD waves. She was also a scientific editor for the Astrophysical Journal from 2017 to 2020. Her hobbies include writing and writing poetry, and she enjoys the parallel ways in which physics and poetry compress big experiential truths into small spaces.
Okay, thank you. So let's make sure my PowerPoint works. Let's see. So I share screen. Go to that slide. Share. Let's make sure this is working.
Yeah, it looks great.
Okay, full screen and everything. We're okay?
Yeah, yeah.
Okay. Let's see. Okay. Okay, so thanks for having me. I don't know everybody's background here, but I was asked to talk about some observations, and I put together some slides. If I don't cover what you're interested in, just ask me at the end. So I grew up in Texas. I just heard somebody was at UT Austin, but I grew up in Texas a long time ago. Um, and I just wanted to point out that when I was growing up, I lived in a small town, and my mom was a nurse and my dad was a minister, and I had no idea that research was possible. I mean, I guess I must have known somehow because I knew there were things like Nobel Prizes, but I went and studied engineering as an undergrad because I thought if you liked math and physics, that's what you did, because a lot of people at that time were studying petroleum engineering in Texas. And I only saw that research was something that people could do as a profession when I got a job at Los Alamos National Lab in the summers. And that's when I really realized that it would be fun to do this. And so I guess that many of you are having your first REU experience, or maybe second or third, and discovering if you like research as well. So it's an exciting time. I love going to Los Alamos. Okay, so this is an image of the sun. It's in a wavelength called 304 angstroms. It's actually an older image from spacecraft SOHO, and it's showing, the sun in a certain wavelength that is about 50,000 degrees Kelvin, and is showing some structure in the chromosphere with a huge prominence that many, many Earths could fit underneath. So I'll talk a little bit about this. And I don't know how much people know about basic astronomical observing techniques. Okay, let's see. That did not advance for me. What's going on? Let's see. All right. So 415 years ago, Galileo observed the sun through a telescope, and he drew sunspot drawings, which were then in his research journal and are shown here, put together into a little movie day after day. And you can see that the spots are traversing as the sun rotates. And I don't know how many of you know this, but Galileo actually got in trouble with the church back in those days and was put under house arrest because the astronomical objects are supposed to be, they were supposed to be free of blemishes. So the fact that he saw these sunspots was heretical, that the sun was not a perfect object. But I like to show that because then I get to show our instrument, which is the helioseismic and magnetic imager on board the Solar Dynamics Observatory. And this is sort of a generation 2 type instrument because the Stanford Solar Group had another instrument called the Michelson Doppler interferometer that was part of SOHO. So this is the last 14 days worth of data seen in the continuum intensity, and you can see the sun rotating, and you can see the sunspots on the surface and some other small features. And this is the layer of the sun that you can see with your naked eye. So it is what's called the photosphere, where the atmosphere of the sun becomes optically thin and the photons can just fly out instead of bouncing around like they're doing in the radiation zone and the convective zone. So you probably know that the sun is a common G2 star, a yellow dwarf. It's a main sequence star, which means it's fusing hydrogen in its core. It rotates every 28 days. It's big, it's old. It's about halfway through its life, about 4.5 billion years old. It's about 5,800 Kelvin on the outside and 15 million Kelvin on the inside. And there's different zones in there. That's the core, the radiative zone, the convection zone, the photosphere. And then as you go outward in the atmosphere, you have the chromosphere and the corona. And this image is from our Coffees project, where we tried to squeeze a lot of what we do into this diagram. It's showing different observations on the solar surface, and I'll talk about those. So the Solar Dynamics Observatory is a spacecraft that was launched in 2010, and it has 3 instruments on board. You can see a makeshift image here of it. This is AIA. This is the helioseismic magnetic imager here, and this is Eve, and you can see the solar panels and the high gain antenna. HMI observes the full disk of the sun, so takes images of the entire disk, not a high resolution field of view. And it's using an iron line at 6173 angstroms. And it has a resolution of 1 arcsecond, which means it has a pixel size of about 0.5 arcseconds. And it's got, it's based on a refracting design, and it's got a 14 centimeter aperture. It's got 4 CCD cameras that are 1024, so all in total, the image is a 4096 image, 4096 by 4096, and SDO sends down about 1.2 terabytes per day. I wanted to mention what absorption lines are. When I say that we're looking at the 6173 angstrom line, that's an absorption line in the solar photosphere. And if you've spent time in astronomy classes, you are aware of this, but I don't know if we have any students that are from engineering backgrounds and don't know about absorption and emission lines. But basically, you can either get absorption lines or emission lines when an electron is changing its location in the orbital SPDF, those orbital layers, levels, I forget what they're called. But that way you can see what the chemical composition of stars are, and you can do a lot of physics by looking at those absorption and emission lines. They're called the Fraunhofer lines because of who first observed them and cataloged this image where you can see all these dark absorption lines in the spectra. And yeah, there's a lot I could say about that, but I'll try to keep it short here. So this is just to, again, to remind you that the absorption lines are basically the, an electron is absorbing a photon of a certain energy and it's changing its orbital level, and then you get an absorption line at that specific frequency. And you also get emission lines if it's the opposite, if it's changing its orbital level and emitting a line. So the different wavelengths basically sample different temperatures and different layers in a star's atmosphere. And I think many of you have probably seen sort of like these images of the Milky Way that are imaged in infrared versus visible, things like that. And you can really see different structures depending on what wavelength you're imaging at. So these are many of the wavelengths that are observed on the Solar Dynamics Observatory. These are HMI, and the rest of these are the atmospheric imaging assembly. So let's see. One of the reason or the way we get to image the full disk of the sun is by using different optics to tune to that specific wavelength. So in this image here, we're looking at an absorption line of the iron, the 6173 iron 1 absorption line in the black line. And then these colored Gaussian-like lines are showing you the tuning that our instrument does. So we actually sample at 6 positions across this absorption line, and our tuning, our optical pieces, will be tuned to a certain wavelength offset from the center of the absorption line, for example, in this yellow or orangey yellow curve. And it's integrating all the light underneath this. So it's not an incredibly precise tuning of the wavelength, but as you go across the line, you're looking at different heights of the line and you're getting different information. And you're also getting to see what the spectral line is doing, whether it's moving due to a Doppler shift or whether it's split due to polarization, which I'll talk about later. But in this way, we sample all these tuning positions in different polarizations, and then we combine them to get the information about the sun that we're trying to learn. So this is an example of an individual filtergram, just one of these tunings. And you can see the 4 CCDs that are put together, the 4 1024 CCDs that are put together to make the 4096 image that we get. So an alternative to doing this, which is tuning to a specific wavelength in your absorption line, is to actually place a slit across an image and send that light to a diffraction grating, which then spreads the light out, and you can get very high resolution for the intensity as a function of wavelength. So that's what this is. This is intensity as a function of wavelength. And this is 2 images sort of put together. It's not the exact image. This is not the exact region that a slit was placed to create this. I just threw them together conceptually. So you can see that the intensity is higher here. You can see the granulation. Those are the different dark and light bands here. And you can see that you're probably in a penumbra here and an umbra here, so dark regions. And then this I'll talk about a little bit later is the polarization signature, which allows you to measure the strength of the magnetic field. So those are two different types of ways that an instrument might sample the sun or other stars using a tuning and a full disk image, or using a larger image that you then get more spatial resolution, or using a slit and getting more spectral resolution. Those are trade-offs. So I wanted to just kind of break for a second and say that I study sunspots. I really love sunspots. I can't imagine not studying sunspots. I'm a little bit bored right now because the sun is kind of being a little wimpy. It's not producing quite as many sunspots as it was about 6 months ago. And I'm kind of like yawn when I look at the sun every day. I want a really big sunspot and some nice flares and coronal mass ejections. But in a sunspot, this is a high resolution image of one. You get basically a sunspot is a strong magnetic field that is cutting through the surface of the sun. It's like a giant rope of magnetism, and it's suppressing convection. So you can see all these convective cells around here, but it's suppressing convection. It's still very hot, but it looks dark and cool to us compared to these regions. And this is the umbra, and this is the penumbra, where the penumbra is also a strongly magnetic region, but not as strong. So it's not fully suppressing the convection, and you can see these fibrils here. Okay, so this is today's sun. Like I said, it's a little bit wimpy with the smaller sunspots, but you can see the connection between the lower part of the atmosphere, which is the 6173 iron line from the helioseismic magnetic imager, and then you can see the connection to the emission in the corona, where you get to see that these magnetic regions are connected by these long hot loops in the corona. And there's also a lot of other nice details that you can see up here of structure in the solar atmosphere. Now, we've talked about looking at the images in an absorption line or an emission line, but there's two other very important observations that you can get just from the light alone. And that's by looking at the polarization signal, you can determine the magnetic field strength. And looking at the Doppler shift, you can see the velocities on the sun. So looking at the polarization, you have to have a filter wheel in your light path that then samples what's known as circular polarization and linear polarization of the light. I'll show you a diagram of what that looks like. And then you can determine the magnetic fields and their strength and their direction. And then alternatively, if you're looking at you can see the Doppler shift. If it's not a magnetic field that's causing the line to shift its position, it's usually the speed, the line of sight velocity of the plasma. And you can measure the Doppler shift, which I'm sure you're well aware of, that's related to this equation. And for example, here's a sunspot, and you can see the light and the dark. You can see that the material is flowing radially outward in the sunspot. So some of it looks like it's moving away from you, and some of it's moving towards you. And you can even see this on the larger picture of the sun. This is a dark edge and a light edge, and this is the sun rotating. So you're seeing the light, one edge is coming towards you in its velocity, and one's moving away. And you can also see a lot of other features known as supergranulation on the surface. So the description of polarized light that I just mentioned, you have these optics in your light path that then can limit whether you're looking at a linearly polarized light. And by linearly polarized, I mean that the electric field vector of that light is moving in one plane. Like in this one, it's moving vertically up and down. Whereas this one, it's linearly polarized in the other direction. It's moving in the horizontal plane. And a circularly polarized light would mean that it's got this rotation. And so you can actually determine the elements of the magnetic field based on the combination of these, the strength and the direction of the magnetic field based on the combination of how much of each of the polarizations that you measure. And we do that through something known as the Zeeman effect, where I don't know how many of you know about the Zeeman effect. You probably do. It was discovered in 1908 with I think it was Gregory Hale. I forget his first name, Ellery Hale. But Hale was observing a sunspot and he was able to see this Zeeman effect, which basically means that the magnetic field breaks the degeneracy of the spin of the electron. And so you actually get two components on either side of your spectral line. So the Stokes vector, I, Q, U, and V, is the amount of polarization you get in the different combinations of linear and circular. And that's how we can tell that a sunspot is a strong magnetic field, and we can get an estimate of how strong it is. And different atomic lines have different sensitivities to the magnetic field. So some are better at measuring magnetic field than others. You have to look at that. It's called the Landé factor of the line. So that's my little blurb on how you measure the magnetic fields. But with the Doppler velocities, you can use those Doppler velocities to you can use them in a tool called helioseismology, which actually is like seismology but of the sun. And you can use there's patterns of how the sun's surface sort of pulses with trapped waves underneath in the sun's interior. And this is an example of these different pulsations of modes that red or blue would indicate like material moving down or up in relation to the sun. And that tells you about the interior of the sun, how dense it is, and what the motions of the interior are. So these are just schematics. I'm not showing you, real data. But the helioseismology has determined the structure of how deep the convection zone goes in the sun, what some of the flows are at depth. So they use different acoustic waves and different motions on the surface to measure different depths. If they're using these multi-skip modes, you can measure shallower, or if you measure what they call a global mode, you're measuring deeper into the sun. So that's been a huge advancement in studying the structure of stars and the sun. There's astroseismology as well, which has made it's done a lot in the last decade or so.
Hey,
There's
Aimee.
yeah.
Yeah, we're getting close to time, so I don't know if you're ready to
Okay.
wrap up.
Are we
But
at
we also
12
have some
minutes or
questions.
15?
Oh, we were thinking around 12:13. Yeah,
Okay, so, well, no, I just didn't know if we were already at 15. But I
I
was just
think
going to
so. Yeah.
say HMI has this 14 centimeter aperture, and DKIST, which is a ground-based observatory in Hawaii, has a 4-meter primary mirror. So there's obviously different instruments out there that have much higher resolution. This is a ground-based one, and this is an example image of what it can see. And so I was just going to mention real quickly, why do we care? Space weather. We got a lot of dramatic events happening to our instrumentation and on the ground due to the sun's energetic storms. And I'll just show you this and we can start to ask questions. This is an old movie where you get to see a proton storm hit the detector from a coronagraph that's eclipsed the sun there, and we get to see the coronal mass ejections that are flying outward. And you probably already know about the Starlink satellites. About 40 of them didn't make it into orbit. They burned up on re-entry due to a solar storm. And then I'm personally very interested in the sunspot cycle and the solar dynamo, but I can leave it there for now.
Okay, yeah,
I'll
maybe we
show
could.
my
That's
image.
fantastic. And by the way, I'll put SDO and Soho have great galleries of that kind of imagery, but I think SDO you can still check live every day, right?
Yeah,
Okay,
absolutely. Yeah, I look at the sun every day.
right, and anybody can do that. I'll put that
Yep.
in the chat. But
I always tell
Claudia,
people it's like a webcam on the sun. Yeah.
oh, it's fantastic. I used to look so often.
And this is a nice movie of a sunspot emerging, a cluster. Yeah.
Great. All right, Claudia, do we have a question?
I'm not Claudia, but we have
Oh, come on, sorry.
we have a question from Julissa, I'm not sure how to pronounce your name. I'm sorry. But if you want to go ahead and read your question out loud, that's fine, or I can read it for you.
Yeah, hi. Hopefully you guys can hear me. It's Julissa. I really like your presentation. Thank you so much, Amy. My question was, why do magnetic field spots resist the upward motion of ionized gas? I think I remember learning about this in stellar something to do with the charge, but I kind of forgot. So
Wait, what is the
thank you.
question again? I heard some background noise. Why do what?
Why do magnetic field sunspots resist the upward motion of ionized gas?
Why do they?
Yeah, I can read it. Why
Yeah.
do magnetic fields and sunspots resist the upward motion of ionized gas?
I'm not really sure of the question. I mean, you mean why is it why is it suppressing convection?
Yeah,
Oh,
basically.
well, the magnetic field has a pressure, and it is so if you combine, so if you imagine that the pressure in the sunspot needs to be equal to the outside gas pressure nearby, um, the magnetic field adds its own pressure. And so it basically becomes like a stiff, um, I'm not describing this very well. It's sort of like a stiff rope that it's resisting. It wants motion along the line of the magnetic field, and it basically has the magnetic pressure that adds to the gas pressure, and so it's less dense in there. And this magnetic pressure means that not all motions are allowed. So there's something called magnetohydrodynamics, which is like regular fluid dynamics, but with all the magnetic field equations, like the Maxwell's equations. And so that's MHD, and MHD has more limitations about how things can move in the plasma. I don't know if I answered that very well, but that's my take at it.
All right. Well, thank you so much, Amy. Appreciate that. And we're hoping to have some more time for Q&A at the end too. So
I'll stick around in here, everybody.
yeah. And again, if you have questions, put them in the Q&A function at the bottom of the Zoom screen. All right. And then Claudia, I believe you're going to introduce Hunter, yes?
Yes, yeah. Please join me
Oh,
in
no, not
welcoming.
Hunter.
Oh, Loren.
Loren.
Yes.
Yeah.
Yeah, all good. Please join me in welcoming Loren Matilsky, an NSF postdoctoral fellow working with Professor Nicholas Brumel at UC Santa Cruz. Loren earned his PhD in astrophysical and planetary sciences from the University of Colorado Boulder in 2022. He graduated in physics and mathematics from Cornell University in 2015. His research focuses on stellar dynamos, specifically how magnetic activity evolves as stars spin down, comparing solar-like stars to fully convective EMS dwarfs. Please welcome Loren.
Cool. Thank you. Let me see if this works. I'm gonna share. Um, hmm. Now I don't see a share button. That's weird.
You're on the
Um,
main Zoom screen. It should be
maybe
the green button at the bottom.
oh no, there it is. Okay.
Okay.
You see the hold on.
There we go. It's loading. Okay. Yeah. Good.
Okay.
Perfect.
Full screen, no Zoom interference.
Nope.
Sweet. Okay. So yeah, thank you for the introduction. I'm also thank you, Amy, because I think there's a bunch of stuff now I can sort of gloss over. Um, but yeah, so what I do is magnetohydrodynamics or MHD, which is just what Amy ended on. And as she said, we combine the equations of fluids, which are basically the Navier-Stokes equations, and then electromagnetism, which are um, Maxwell's equations. And then these equations are numerically integrated forward in time using supercomputers. So this is why it's a computational theoretical simulation of the solar interior, but really what we're thinking about is a spherical shell of fluid motion inside a star that's magnetized. And so this is one of my simulations where we're looking at the different fluid flows um, on spherical surfaces, and then there's like these meridional cutouts. And so this is the outer part of the sun where there's a bunch of convection, and we're showing basically the curl of the fluid velocity, the vorticity up above this dotted line, and then below the dotted line is a poloidal magnetic field. And so the central idea is to simulate the dynamo, which very basically is how does this small scale turbulent motion in the outer part drive a large scale magnetic field. And that large scale magnetic field is ultimately where we think these sunspots um, come from in the first place. And so that's why I think that the dynamo is really important. And then there's something else called the tachocline, which I will explain in a bit. But these simulations self-consistently establish a shear differential rotation. And let me move on so we can get through things. Okay. So these are the equations, just in case you've seen vector calculus, and this is to convince you that you need supercomputers for these because they're nonlinear. There's a bunch of them, they're coupled. You have huge separation of time scales and length scales, and so you need to integrate them on a computer. Even then, the true equations are difficult, so we make some approximations. It's called the anelastic approximation, and so you assume a bunch of physics, and it makes it slightly simpler, but you still need a supercomputer. And if you have access to a few thousand cores, then you can download this code on GitHub and then reproduce all the stuff that I'll show at the end. Okay, why do we care about any of this? Well, we have the sun, but the sun is a star. And if you look into the night sky, then you have a bunch of stars, and they're all different colors and different brightnesses and different distances away. And if you just look at this, you want to study them forever. I think like Aimee wants to study sunspots forever. I want to study stars forever. And stars are interesting because they're the oldest branch of astrophysics. And they're the building blocks of the universe. And we used to think we would never know anything about them because they're so far away. The sun is super close, but other stars are tiny pinpricks. And so this is one of my favorite quotes from a French philosopher. There's a lot going on here, but we'll never know what's inside stars. And then no one knew if they were solid or not. And so he basically saying there might be aliens on them. And this was just less than 200 years ago. So we went from, a century or so really not thinking we would ever know anything about stars to knowing a whole bunch about stars. And the way we do that is, as Aimee was describing, spectroscopy and absorption lines. And so each star has basically a chemical fingerprint. So Aimee showed the one for the sun, but you can do this with any star that you can see. You can shine it through effectively a prism, and then look at these absorption lines, and all these different lines correspond to different chemicals. And so it's kind of like your fingerprint makes you unique. These different absorption line structures, no two are the same, and so it makes a star unique. And what's really interesting about all the stars is that they're organized into a very compact diagram that illustrates how stars evolve over time. So where the sun is on this plot is, well, first you want to plot things in as confusing a way as possible because we're astronomers. So temperature goes in reverse to the left, but then the luminosity goes up. I don't know how many people, I don't want to be preaching in the choir here. Anyway, you're plotting luminosity and surface temperature of a bunch of different stars. And what you find is that luminosity goes up with surface temperature. And so that's what determines these different colors. So it's also called a spectral class. And it's basically blue or the hot stars. So when you look in the night sky and you see blue stars, they're hot. The sun is relatively cool slash mid temperature, and that's why it appears yellow. And then you have all types of different stars, and they mostly occur on this main sequence for much of their lives. And then there's other stuff as the star evolves in late stage before it dies in supergiants and red giants. And then if you get confused by the temperature, you can also just scramble up all the letters of the alphabet and then do O, B, A, F, G, K, M, which is just a historical artifact. Okay, so there's a lot of structure, and part of the reason, I guess, where I'm going with this is that part of the reason we want to study the sun is to understand stars more generally, because the sun is the only star that you can really resolve in high resolution. And so this is similar to something Aimee showed, but I think this is near solar maximum, so Aimee will be happy. And you can see a bunch of magnetic activity in these latitudinal bands. I won't go over this because the sun is basically its energy is produced by thermonuclear reactions in the core, and then there's a stable layer where there's little motion of the fluid and things are transported outward, and then basically all the action is in the outer 30% of the sun where there's a convective zone. And the convective zone is what drives everything. And so those sunspots that Aimee was showing have a number, I'm not sure, well, anyway, I'll go through them again. There's a bunch of different rules for how the spots emerge because they usually come in pairs. This is all called the solar dynamo problem because ultimately these spots come from the large scale magnetic field, and how the large scale magnetic field is so ordered is, I would call it the central question of solar physics. Although maybe there's some other stuff because it really is at the heart of everything. It's the solar wind, space weather, everything in the heliosphere is really driven by the magnetic field. And if you look at the dynamo and you categorize the spots, you see a bunch of different patterns. So first you can look at Hale's polarity rules. The spots come in pairs, and then the leading spot is opposite polarity in the northern and southern hemispheres of the sun. Every 11 years, these polarities reverse. So what's being shown here is the famous butterfly diagram, where you take a longitudinal average of magnetic field. Here it includes the polarity. So those leading spots show up a little bit closer to the equator. That's because of Joy's law. The spots first appear at 30 degrees, north and south, and then at sites progressively closer to the equator. And this is why they make a butterfly wing. And so it's called the butterfly diagram. And every 11 years, there's these Hale's polarity rules between north and south, but then each polarity flips. And so there's a 22-year cycle from start to finish that includes two of these butterfly wings. And then simultaneously at the cycle minimum, there's all this flux of the opposite sign getting transported to the pole. And so this is basically the sun is trying to tell us something about the interior magnetic field, and answering that question probably in parallel with the Earth's geodynamo, because the Earth also has a dynamo, which is not ordered like this. So the north and south pole of the Earth, for example, flip chaotically once every 100,000 to a million years. So not all things look like this. And the question is, why is the sun so ordered? Okay, and then finally, the other ingredient, you have the convection. You also have large-scale shear. And so Aimee also mentioned um, the signature of seismic waves at the surface. You can look at intensity or the Doppler shift of different spectral lines. And there's a huge wave field. So my thesis advisor described it like a giant bell that's ringing at all these different frequencies with different standing modes. And And what's cool about the sun, again, different than the Earth, is that, well, it's good because, I mean, these modes are acoustic oscillations, which on the Earth are earthquakes. And there's only a few of the lowest order harmonics that occur on Earth, whereas the sun is ringing with 5 million of these all at once. And anyway, you can use those to probe the rotation rate of the sun. And so that differential rotation that Galileo observed, um, that's the red. Red means fast rotation, blue means slow rotation in this plot. The solar equator is here, rotation axis is here. And so that differential rotation um, occurs all throughout the convective zone. And then at the base of the convective zone, there's a very sharp transition between differential rotation, fast equator, slow pole, to rigid rotation below. And that's basically where my research has wound up for, I don't know, the last 5 years. This is called the tachocline. It's believed to be extremely important for the dynamo because the shear is so strong. And understanding how it can exist in the first place is, I mean, that's basically what I've done. It's all of what I've done as part of Coffee's formally. Um, and yeah, I don't know. Why do we do this? Whoops. What do we get out of this? Mainly, we expand the frontiers of our curiosity. I think that's the main thing. I mean, this should be reversed on a NASA grant. I mean, we do want to predict space weather, and you need to understand the dynamo to do it. But this is why I do it. And then you get glory if you figure something out, then everyone thinks you're super cool. And the way you do that is you publish papers. And so these are a bunch of different papers that have come out of this work. And this is the draft version of a new paper that I'm very excited about. This new paper is the one where I'm showing the simulation results. So anyway, yeah, stars are really important. The sun is the only star that we can observe, and we need to use huge supercomputer simulations and fund the agencies that provide those facilities far, far into the future. Okay, that's all I have.
All right. Thank you so much, Loren. That was great. You actually, I was going to ask you a question. You kind of alluded to it here. I was going to ask you, modeling is considered successful when, say, a prediction comes true. Is there any prediction from modeling that you know of that actually is either well known or most impressed you or something of that nature?
Oh, that's a good question. One thing, I mean, really the surface stuff is that, first of all, the theoretical models are not, they don't have predictive power.
Hmm.
People on coffees might disagree with me, but that's my firm belief is that we're doing this to figure out how things work more generally. Um, One thing that I thought was really cool, I don't know, maybe Aimee knows more. I think there was the seismology was able to like detect an active region on the far side of the sun, and then it was there. I mean, that's more of an observational thing, but I mean, the theory of the P modes is essential for that. Oh, actually, you know what? The huge thing that started all of this was the solar neutrino problem. Um, so that is like a really big history to this because basically the temperature from solar models was determined to be 10 million degrees Kelvin, and that predicted roughly 3 times the number of neutrinos than were observed. And so there was a missing 2/3 of the neutrino problem of the neutrinos. And a lot of people were like, maybe these models are inaccurate, and that temperature is wrong. And so the temperature is lower, and there's not as many neutrinos. And then seismology was so precise that it was like, no, that temperature is accurate to like 1 in 10 to the 4. Um, so that was honestly, from a funding perspective, how all of this started because, convinced NASA to launch a billion-dollar observatory into space
Right.
to just look at the P modes.
Right. Fantastic. Okay. Well, thank you so much. Really appreciate this. Let's see. We are definitely moving on to Hunter and Phoebe. You're going to introduce.
So our final speaker for today, we have Hunter Kanniainen, who is joining us to discuss heliophysics instrumentation. Hunter is a mechanical aerospace engineer at UC Berkeley Space Science Laboratory, and he previously worked as the lead design engineer for NASA Ames Tech EdSat small satellite team. He's skilled in utilizing SolidWorks and CAD for instrumentation and design, and currently is a mechanical engineer and project manager for the Focusing Optics X-ray Solar Imager known as FOXY. And FOXY 4 just launched it last year in April 2024 and successfully imaged an M-class solar flare. Please welcome Hunter.
Thank you. I love it when the introduction allows me to skip a couple slides, like you covered a lot there, so thank you. Let me go ahead and share here. Let me know if everyone can see these slides.
It's loading. Yep, got it.
Looks good. All right, great. So yes, hello, my name is Hunter. I'm going to talk a little bit about instrumentation, mainly focusing on the FOXY 4 project. We've heard a lot of science so far, so I'm going to kind of skip through some of the science slides that I normally give, and then focus a little bit more on the technology side of things. It is not clicking on the right thing. There we go. Skip through this. We got that in the intro. I did CubeSats at Ames for a while, but there's no science background to this. This was all engineering work. So now that I'm at the Space Sciences Lab, I get to work on science missions. Again, the one we're going to focus on here is the FOXY 4 sounding rocket, but here at the Space Sciences Lab, we do lots of other kinds of projects as well, from small explorers, mid-X missions, and balloons. So what I'm here to talk about, especially because it's a Helio mission, is the FOXY 4 sounding rocket. This was, the FOXY 4 mission was PI'd out of the University of Minnesota by a very talented professor there named Dr. Lindsay Glesner. The FOXY 5 mission that we're now currently working on, the PI ship is here at the Space Sciences Lab. But here we see some photos, both at the Space Sciences Lab, at the White Sands Missile Range in New Mexico, and then Poker Flat Research Range in Alaska that we launched. So these are the ones that I'm going to go kind of quick through. Why solar flares? All processes of solar flares happen in an environment of plasma. Plasma makes up the vast majority of the universe, and we'd like to understand how this plasma behaves, because it can answer questions such as space weather and can also be telling about lab plasma applications such as clean energy. So that's what FOXY is here to do, is understand some of the more extreme conditions of these plasma behaviors in solar flares. So what are solar flares? So stars, in our case the sun, have nuclear processes that are constantly releasing concentrated energy outward. And this energy not only follows the magnetic field lines that tend to lie on the interior, but also kind of reshape and warp these field lines. This is a quick movie showing the movement of these field lines within the interior of the sun, and mainly pointing out that factors such as this energy being released outward and the rotation of the sun starts to really reshape these magnetic field lines. And if I'm good with when I pause this, you'll start to see here on the right side of the image, you start to see that there's times when these magnetic field lines actually exit the interior and extend into the corona. And I don't know how well you can see my camera, but I have like a cable here. And what you tend to see is that the difference in density from the interior to the exterior can actually start to twist these field lines. And you get something special here when it twists and it reconnects back to itself. That's what we call magnetic reconnection. And this is kind of the catalyst or the explosion point of the solar flare, where the stored energy is being converted to particle energization, direct plasma heating, several types of waves, and energy moment transfer. And it's this part of the solar flare that FOXY is trying to image with direct focusing techniques. And that's the really important about this, is that solar flares have been observed in the past using indirect focusing, but it's the direct focusing that FOXY really intends to use here, which is where we get into the more special technologies that were used. Sorry. So something that we see in Newtonian telescopes is that we use a parabolic primary mirror and then a hyperbolic secondary mirror. And this works great with visible light because the light likes to bounce off of these mirrors. This becomes an issue when you're trying to image X-rays, right? So X-rays have a very short wavelength on the scale of atoms. So X-rays like to pass through a lot of materials. You can kind of trick the X-rays and you can actually get them to bounce off of mirrors if you have a very, very shallow angle. This is great, but how do you apply this to a telescope that is actually going to take images? Well, we have something called a Walter 1 geometry telescope that still uses a parabolic primary mirror and a hyperbolic secondary mirror, but you have them kind of in sequence with each other, and you kind of have a straight downline view where you have a single reflection, double reflection, and then your focal point, instead of being an eyepiece, is a detector at the end. It's creating optics that use this Walter 1 geometry to create the telescope that is kind of the bread and butter of the direct focusing of the FOXy mission. Just as a quick example as to why direct focusing is so important, there's a comparison here between the data from RESI and the FOXy 1 mission, RESI using indirect focusing, FOXy 1 using direct focusing optics. And here you see quite a difference in the noise that are in the images. So the pieces of the FOXy rocket, the left side image there is a view of the CAD model of the experiment section of the FOXy 4 rocket. On the right side, you see it integrated with several pieces of the sounding rocket that we connect to. This does not show the motors of the rocket, but just the telemetry sections, the recovery section, and then the experiment. I was showing those optics a moment ago. There are 7 of these Walter 1 optics modules at the front end of the FOXy payload. Some of these come from NASA Marshall. Some of these come from Nagoya University in Japan. And then we have a set of heritage optics that were flown on previous FOXy missions. These also come from Marshall, but are older versions of the technology. And then this optics end also has things like an aspect camera and some NASA sensors that are used to co-align us with the sun. On the back side, we have 7 detectors. 4 of these are hard X-ray detectors of cadmium telluride. These come from some of our collaborators in Japan. We have 2 soft X-ray cameras known as CMOS detectors. These also come from a group of collaborators in Japan, but different section. And then we also have, new to FOXy 4, is 1 time-pix detector. This was developed here at the Space Sciences Lab at UC Berkeley. All of these have to be cooled pre-flight and remain cool during flight, so they're inside of a cryogenic chiller plate. And then there's a lot of readout electronics on the backside for us to be able to store and send down all of the information and images that we're taking. As I mentioned, that there's very shallow angles of attack on these mirrors. So there has to be quite a distance between our detectors and our optics in order to create a proper focal length to focus. In the case of FOXy 4, this is a 2-meter focal length. For FOXy 4, it was a very big undertaking. There were several different international collaborators, several domestic as well. It was a massive team. You get a view of just the people who showed up to the Poker Flat research range here. The team is actually several times larger than that. So it's a big undertaking to set up an instrument like this and get everything working all together. The launch site was selected to be Poker Flat Research Range. A fun fact about this is when they were selecting the launch sites, the principal investigator, Lindsay Glesner, was really trying to set up a mission that they could launch out of the Kwajalein Atoll, which is an island in the Pacific, because they were like, this would be a great excuse to have an island getaway. Turns out that imaging solar flares is not great from Kwajalein, so instead of an island getaway, we got northern Alaska in early spring. So we got snow instead of sand, but it was still remote, I guess. The FOXy 4 campaign was special because we flew alongside another solar flare-centric sounding rocket known as High C Flare. This was based out of NASA Marshall, and we flew one right after another. On the right side here, you see a group of just the FOXy scientists and engineers that were preparing down on the pad in front of the rocket. Another fun fact about the FOXy 4 campaign is that it's quite difficult to predict a solar flare. It's kind of kind of impossible. The best you can do is work towards flare prediction techniques and just try to use the prediction softwares that we've developed that give you the best results. So there's multiple types of categorizations for solar flares, B, C, M, and X. Based on the criteria that the scientists set, Foxy really needed to view an M-class flare. An X would just be too much, and then a B and C would kind of get filtered out. So an M-class flare was really needed. And because of this, we had a 2-week window of several hours a day that we were able to be there. And if we didn't make it within that 2 weeks, Poker Flat would have shut us down for pretty much a year because fire restrictions and everything stop summertime launches and it gets too cold in the dead of winter. So it would have been a very long delay in the mission. So you have to wait and wait and wait a very long time for the perfect conditions to hopefully get a trigger to go on one of these flares. It was not until the second to final day of this 2-week launch window that Foxy finally got a promising enough flare prediction to go ahead and launch on. And we got to launch our rocket. 60 seconds after our launch, High C Flare also launched, and this was a very successful campaign. Now, this was fun because you get to launch these rockets and you're all excited about the data and it flew, but then you have a very big issue of we don't know until later if we actually caught a flare, which was part of our comprehensive success criteria. So it was still silent in the control room for quite a while until we got a thumbs up from our PI, Lindsay Glesner, that Foxy did manage to observe the predicted flare, and we got to take images of a class M1.8 flare. Here you see some quick look images of both the soft X-ray detectors and hard X-ray detectors at the active region of the solar flare. So this was very exciting. There's more information coming out about this. If you guys follow the University of Minnesota and the Space Sciences Lab information on Foxy, more images are coming out in the future, and a lot of upcoming conferences will have speakers speaking about Foxy. And then the last thing I wanted to point out here, which is just something that happens sometimes when you develop suborbital missions. Foxy 4 came back down a little while later and landed on the side of a mountain in Alaska. It had a very rough landing, and then it decided to slide down like a NASA bobsled about 200 meters and destroyed part of the skins, damaged some of the optics. All of the detectors were very good, but we have some reconstructive surgery to do before we fly again later this year. But Foxy 5 will be flying again. Our first launch window is November of this year out of the White Sands Missile Range. So that's my sections on technology and instrumentation. Thank you.
Wow, exciting. Thank you so much, Hunter. Really appreciate that. And you kind of were just spot on as what I was hoping for here, showing that, engineer, when it comes to scientific research, especially in today's technological advancements and such, that engineers are just as important as the science side. So thank you so much. I know it's time, and we're a little over time, but I'm happy to stick around. But if our speakers have to go, it's okay. We understand. But for anybody who can't stick around, we're happy to try to answer your questions as best we can. And Kamal, looks like we have a question from Sophia. Sophia, are you still there?
Still here.
Oh, yeah. You want to just ask your question live?
Yeah. I got to meet Lindsay earlier in the year at University of Alaska Fairbanks in the Poker Flat Research Range. We actually went to Poker Flat and we're all around it and whatever, and we saw all of the old scribbles still on the whiteboard during troubleshooting. But she showed us the launch video, and I got so anxious watching it. Even though I knew it launched, we were all gripping our chairs and all that. And I am maybe not so much a science question, but what was it like for you, during the moments before the launch and all of that?
Yeah, that's a good question. It's kind of a battle between myself and the scientists sometimes, because the experiment portion of this payload is like my baby for several years, right? And I just want to see this thing launched. And I totally understand the hesitation of the scientists on making that decision, because as much as they want to see it launch, they only want to launch if they know that they're going to get the results that they can get. But I'm the anxious engineer over here, just wanting to see this thing go up after so much time. So it was very stressful. And I don't know which video you saw, but if it was the one taken outside, you may have heard my voice in there just telling this thing to go. But
It might have been.
it totally might have been. No, it is very stressful. And you want this thing to be successful. And the hardest part about this is if you're not down in the building that the NASROC team who manages the launches, where they're at, these pauses happen and you don't know why these pauses are happening. So you don't know if it's maybe an issue with your experiment section, if there's an issue with the cooling and there's damage to your detectors, if there's just an issue on their portion. And this is there's so many concerning things, and I think the worst part about it is being completely in the dark. It's also extra scary because you're on your final to last day, or your second to last day, and then you know that it could be a wash, and you wait a year. So it's very stressful, which I think makes it far more emotional than you expect it to be when it finally does launch. I mean, I think everyone was just generally excited that when it did launch, and then when Lindsay gave the thumbs up that they actually caught the flare. I think some people were like screaming in excitement and some people were crying, and there was probably a good portion of us that was like an ugly combination of the two. But no, it really is exciting. It really does pay off all of that fear. But I like to think that if you didn't have that type of stress, if you were kind of a robot going through it, you're in the wrong field. You know what I mean? You got to be connected to what you're doing. So,
Oh, thank you.
of course, glad you got to see that.
Exciting. Yeah. Loren, Aimee, I have a question for you about this blaze star, T Coronae Borealis, predicted to show up in the night sky again. Do you know anything about that from a modeling perspective?
What is it? I'm sorry.
Have you heard of the blaze star T Corona Borealis? It's a
No.
white. I think it's a white dwarf or a nova that kind of every so many years reappears in the sky. It's supposed to appear in the sky in 2025. I don't know if you know anything about it that you can share.
But it's an aurora?
No, it's just named that. It's a nova star. It kind of goes
Right.
it goes through periodic bursts. A recurrent nova is what they call it.
Right. I don't, but I
Okay.
assume it's related to the magnetic field. But I don't know.
Yeah. It's not our sun, obviously.
Yeah.
Is it supposed to be naked eye or no?
Yeah, exactly.
Is it supposed to be naked eye?
Yeah.
Oh, what's it
I'll
called
put a
again?
link. Well, it's got different names. The Blaze Star, also known as TCRB, T Corona Borealis.
Okay,
I'll put the
I'll look it
Wikipedia
up.
right here. Yeah. I was wondering, I'm just thinking of it's originally obviously seen through observation, and then now it's being predicted to go off again in 2025. So just from a modeling sort of aspect, I was wondering if you knew anything about it. But let me put it in the chat here. So many buttons now in Zoom. All right, there. You can read about it.
Oh, it's a binary star.
Yeah.
It gets material from the other one.
Right.
And
Doesn't that mean one is a white dwarf and
maybe
So
I have to read
white
it.
dwarf, red giant binary. So I think it's driven by the accretion flows.
yeah, but one's constantly sucking material off the other
Yeah,
and then explodes, and then the whole process starts over again.
Yeah,
Anyway,
yeah. No, that's it looks like one of the first examples of that where the star overflows its Roche lobe and then feeds the other one.
okay. Yeah, we were talking about predictions earlier, so that just popped in my mind. All right. I think Sophia, you're the only student left here.
My bad. But yeah, thank you guys. I will say I don't know too much about T-Core Bohr, but I had to talk about it a lot when I was doing open night shows. So I've been saying that it's gonna go nova like for the past year. But yeah, if you look at Corona Borealis, there should be a star that just appears that wasn't there before. So we're all supposed to like keep an eye on it, apparently. But
How long is it supposed to be visible?
I think it said only a couple of days.
Oh, okay.
But I'm not too super sure. But yeah, thank you guys for everything. Bye-bye.
Yeah, thank you so much. All right.
Thanks.
Well,
That was fun. Bye.
yeah, no, we really appreciate it. Thank you so much.
Okay.
Take care, everyone.